scale optimization.
Yes, this is the same talk I gave in San Diego this summer. So if you like, do you know it's a no waste policy I'm recycling. And so also I want to apologize because being a local, just right after that I have to dash out for a meeting. So thank you for inviting me to this workshop. So I want to tell you a little bit about a very practical problem that I've been encountering in dealing with practical uses of optimization, which is basically the idea that optimization problems usually do not come in isolation. It's not as a single instance, but most often it's multiple instances. And how can we exploit the available structure, if any, to go faster and solve these problems with multiple instances? So here's an example. Here's a famous problem in statistics, which is basically least squares, and then there's a penalty for sparsity. So this is the famous LASSO problem. In many cases, you might want to solve the same problem with the similar response, but different matrices. All these matrices are just a rank 1 modification of the same matrix. So obtained by taking a big data matrix and removing, say, one or a few columns. In resource management, often we might have a linear programming problem where this vector might represent demand, and X is an allocation of resources, and C might represent a cost, which we want to minimize. And the network of the distribution of the resource problem is always the same, but the demand changes or the cost changes or both. So further, here is an example that's a more elaborate example from statistics, which basically takes a covariance matrix, an empirical covariance matrix typically, and tries to represent its inverse in a sparser form. So it's a sparsification of a graph. Here X is the estimate of the new covariance matrix whose inverse is sparse. You might wonder why sparsity of the inverse has any interest in statistics. It just means that the conditional dependent structure of the graph is now sparse if X here is sparse. So solving this problem is challenging for large networks. So here there is an approach, an algorithm that has been proposed, which basically takes every node and regresses it against the other. Every node is a random variable, and you regress in a sparse way. That's the LASSO problem. Now here the problem is that these matrices, from regressing one node against all, and then you go on to the next node, the matrix doesn't change much, just a rank 1 modification. So here's a more recent application of the same kind of problem where you have multiple instances of similar problems. This is an approach where essentially we're trying to estimate a sparse distribution, variable p, given some knowledge about moments. So you have linear constraints on that distribution, and you want to minimize the cardinality. If you use L1 norm technique to solve this problem, where you don't get anywhere because the L1 norm is just 1. So it doesn't allow you to encourage sparsity and turn the crank and get a sparser and sparser distribution. So a new approach has been proposed where basically you solve these problems, but each problem from one instance to the next has the only difference is the cost changes, and here you're maximizing one particular index of the variable, and then you go on to the next variable. So these problems share a lot of structure. Okay, so we can be all convinced that there is a lot of applications of problems where you have similar instances that differ by just not much. Here's another example from Emmanuel Candace and his co-authors, where you have to solve some kind of sparse estimation problem. And again, now you're fixing some value, a specific index to 0. Okay, so there's a lot of tasks like this where the problems have a lot of similar structures. Now, what can we do? beyond multiple instance, well, if we just have a multiple instance problem, I don't know, but in addition to this, there's structure. For example, here is an example of a multiple instance, but here all we're doing is varying the parameter of the penalty. It turns out that in many classes of practical applications, this matrix has low rank, or some simple structure, or close to low rank. So how can we exploit these two? The multiple instance aspect and the low rank aspect. That's the focus. Now, why do I say that many problems have a low rank structure? The problem that I'm outlining here actually comes up in text analytics, for example, when you're trying to classify documents. And these are renditions of illustrations, essentially, of the fact that the data that comes from these text classification problems has a lot of low rank. So these are very large matrices. They're very sparse, but still their rank is close to being small. These two graphs explain that, show that. So in robust sketching, the basic idea is you want to replace a problem which involves here convex, typically a loss function. Here is a linear operator containing the data. You want to replace it by a low rank matrix. Why? Because then you can go faster at solving the problem. If you just do brutally that replacement, then it's not doing necessarily what we want, because that procedure introduces noise. And so the robust sketching idea is to go beyond sketching, which is compressing the data into a simple structure, but to take into account the error induced by the sketching. So here, this is the paradigm that I'm proposing, where we start with this problem, and A is low rank. Then what we do here is address here a proxy for this, where A is replaced by B. A is replaced by A tilde, which is low rank. And in effect, this bound is reflective of the fact that A tilde is just an approximation of A. And therefore, A is within that set. A is one of the B's. And therefore, this takes into account the error made by replacing A with A tilde. So this is a bound on this problem. And it induces a way to exploit the fact that A is close to low rank, but not forgetting that we have made an error in that matrix. So the short story is that there's multiple ways to apply this paradigm. And in what we have observed, we can show that we can dramatically reduce computational time. In addition, when you're doing optimization problems, we can guarantee the feasibility of the approximate solution. Okay, so I'll focus first on sparse learning application, where basically these are often without constraints, or the constraints don't have data in them. And it's an easy case. The harder case is when you have a resource management problem, for example. When you have constraints, you have to satisfy them. So just brutally replacing the data in your LP by another will not just generate a feasible solution for the original problem. So here again is a text analytics example. I'm not going to comment on that graph, just to be saying that in text classification, for example, there's a lot of need for solving very large statistical problem with low rank and with multiple instance. So the idea is this. Imagine that we want to solve some kind of sparse classification problem. X is a very large, close to low rank matrix. And we need to solve this problem in multiple instances. That is, maybe we have different y's, okay? Many different y's to solve, or many different lambdas. So it makes sense to spend some time to prepare the problem and approximate this guy with a low rank. That has a cost, but it's like a preloaded cost. And once that approximation is ready, we implement a robust sketching idea for each instance. So in this idea of topic imaging, which I won't comment much, it's basically about understanding how a certain topic is treated in a large set of documents. Then X here is a rank 1 modification of the whole data. It's the whole data minus one row, basically. And the whole data set, which I call X tilde here, is very close to low rank. And Y is essentially extracted from that one row that you remove, and basically that's the problem we end up with. So what we do here is we say, well, let's replace X by its low rank approximation, and then take into account the error made. Epsilon here is the estimate on the error made. So that estimate, basically computing this low rank approximation and that number, is done before any application. So we just take the whole data set, we do that. And then we solve this problem each time we have a specific instance to solve. This results, in this case, in a very simple modification where you have a term here that involves the L2 norm. This is an elastic net, as it's called in the field. Now, this problem has a lot of structure because this is low rank. You can readily see why it's possible to solve it much faster than the original problem if the rank is low. Why? Because evaluating subgradients of this function here is very fast. In fact, this matrix vector multiply, it goes linearly with the size of the problem, with k fixed. So, yes.
Going from one line to the next, is that heuristic, or are you saying there's a...
Thank you. No, it's not. It's an exact, this is not hard to show that this thing is exactly that. Yes, it's a good point. So here is just a little remark to say, statistically, this approach simply entails brutally replacing the data matrix by its low rank approximation. Remember, before we had X here, the original data, and then adding a little term that takes into account the error. So it could be a heuristic. In fact, it's a natural thing to do without the theory, right? What this epsilon does, this elastic net term does, is allow you a much better control on sparsity. What happens is this. If you didn't have this term, and K was the rank of this matrix, you can show that just solving for the first two terms, this is due to my student Vu Pham, recent results shows that in fact you cannot, your solution will be at most K zeros. So meaning you don't control the sparsity. So here's an illustration for the case when the data is rank 1. This is the case when we don't take into account this error and we try to improve the sparsity or control the sparsity with this number here. As lambda grows, there's more and more sparse. But in fact, what happens is that all the components are 0 except 1, and then it dies out. So basically, the sparsity is just 1. There's no control. Whereas here, with the other term, you control better. You're allowed to choose that sparsity. It's just a side remark. I'm just not saying this as a central piece. But just to say that brutally replacing in those statistical problems the data by its low rank approximation has a benefit. It brings you speed, but you lose something statistically. Now, the main result is that this problem also can be solved very fast. So, in fact, you can analyze a little more, and you can decompose this problem into two problems, one involving one dimension, the row dimension, and the other the column dimension. So you solve two problems separately, and each one is much sparser to solve than the original problem. They look like LASSO type problems, and I won't go into the details. So the net result is that you gain one order of magnitude if n is the number of variables in this problem, this number of variables in W, which is typically very large. For example, in text analytics, what W is the number of terms that ever appear in your whole corpus. So it could be 100,000, a million. If you take multiple terms. And so this is usually a problem where the number of variables is very big. And in effect, this whole thing says that if you have here a rank K matrix, then the complexity goes down by 1 order of magnitude. Now, again, I want to emphasize the multi-instance requirement. You can always do this on a single instance, but it really makes sense and is beneficial when you have many instances, because the work of forming the low rank approximation is then just a one-time thing you do, and then all the other instances of the problem will involve either the same low rank approximation or just a rank 1 modification of it. So here's the gain in computational time, where we look at the ratio between solving the original problem and solving a robust low-rank version. So basically, essentially what this graph tries to show is a theoretical bound versus, on synthetic data, an experimental bound. And what it shows here is that there is an order of magnitude benefit to this whole thing, all right? So this is just from one instance. So if you have multiple instances, this is also even better, because the work you do spending on getting the low rank approximation is done once and for all.
Question?
Yes.
I don't understand the term sketching. In what sense is it sketching?
Yes. This is a computer science originally a term that essentially, sketching, we know what sketching is, just making a drawing that summarizes a little bit the scene and doesn't fill in all the details. And so the original idea was in databases, they would, for example, do subsampling. That's a particular kind of sketching where you reduce your whole data into a simpler form that is supposed to be some kind of sketch. And the low-rank sketching is a particular instance of that, where you approximate a matrix by its low-rank approximation.
Oh, okay. So
it's just approximation.
Okay. Yes. That sketch. Okay.
So we did some experiments that purport to show that not only you gain computationally, but you don't lose on the quality of the results. So I'm going to be very quick, because you might not be interested in machine learning and so on. Maybe you are, I don't know. Yes.
Supposedly this would work too with sparsification instead of taking low rank.
Yes, I'm mentioning this at the end, yes. But I've not done that because I have yet, this is an appeal to the audience, if you have a data that is dense, and that's huge. I have not found a problem. I think in MRI they have stuff like that, but it's kind of hard to find an example where you have a huge data set, a very dense matrix, and then you want to sparsify it.
And the robust problem is tractable in the same way with L infinity?
Yes, L infinity norm will appear. Yes, that's a very good point. So what these experiments show, you can focus on one of these curves corresponding to two data sets. Basically, we're trying to approximate the data, and the data, it's not a simple, or it's kind of large scale. Basically, we have 20,000 documents and 40,000, so 20,000 columns and 40,000 rows. It's not trivial. And here we have 28,000 columns and 49,000 rows. So it's a big matrix. And we approximate it by rank 5, 10 to 50. So it's a very low rank approximation and very fast to compute with power iteration, And here what it shows is that at rank 10 or so, we recover the same statistical performance. Remember, this is a sparse classification task. So in other words, there is a statistical performance associated with solving the optimization problem. It's not just we want to solve the problem. There is an end task. And this graphs measure some kind of statistical performance level. And so this red guy here, this dot, is what you do if you don't do any compressing, robust sketching, nothing. You just solve the problem. And we recover the same performance at rank 11 approximation, okay, or so. So actually, I'm sorry, it's not rank 11. What I'm trying to say is that about rank 50, we recover the same performance with a, here's the training time. So in other words, we can go much faster, but we also benefit from the fact that we reduce the rank of the matrix in a robust way, allows us to deal with the noise present in the matrix. So these results here are just yet another application where we're now trying to extract words that are predictive of a certain theme. And for example, in a PubMed data, we're trying to extract words related to cancer, and those are the words given. Using these methods, and just to say that using here a low rank approximation for a very large matrix, 20 is the rank we use. So it's an extremely low rank, and still we get good words, words that are make sense. Okay. All right. So now I'm going to close the topic on application of this robust sketching in statistics. This is the easy part because we have no constraint. Now, how about when you need to solve a large linear programming problem, and it turns out that A has close to some structure like low rank? If you just replace A by its low rank approximation, then this approach miserably fails. In statistics, it doesn't, because you're just dealing with the objective function in which you replace data in the objective. So objective degrades and so on. But here, feasibility is impacted in the sense that if you brutally replace this by a low rank approximation and solve the problem, in most cases, it might not be feasible. And even if it is, then you end up with an X that's not feasible for this problem that you started with. So your solution you're generating that way is nice, but it's not feasible. But yes?
Yeah, just before you go on, so just to get, I'm sorry, to get oriented. So the low rank helps you because you're actually doing a matrix inversion in the other optimization problem?
Okay, good question. Yeah, you're asking how to exploit the low rank structure.
Yeah.
So either, yeah, it's a very key point, because either you view this as a,
If you use like a power method, are you doing an axial inversion here?
No, not an inversion, but imagine just computing the subgradients of this operator. It involves matrix vector multiplies with low rank matrices. So that's the high level reason. But that approach really asks you to use a specific algorithm, go inside the algorithm and change that thing. Or you can analyze this, and using duality, you can reduce the problem in a very explicit way. So then this is algorithm independent here. In other words, you can exploit the low rank either at a very high level by looking algorithmically you go inside the algorithm, or if you want to go outside the algorithm, you can still reduce the complexity explicitly.
Okay.
I prefer this method because it's algorithm independent.
And if you say like the rank is 50, what if the matrix was sparse, that only had 50 non-zeros per row? Would it be better to use the low rank thing or the sparsity structure?
The text, I don't have a theoretical answer to your question, but in the text applications, typically matrices are very sparse because most documents don't contain most of the words. So they're extremely sparse and yet a very low rank structure. But obviously it's much faster, yes.
Okay.
Also, you could do sparse low rank. That's another thing. So I think I need to wrap up. But essentially, I'm going to sketch what I'm trying to say. Now you get the idea. Is instead of replacing A in an LP by its low rank counterpart, you do take into account the error, And what entails is you apply this robust idea where you essentially say that for some delta, this expression is nothing else but A. So A is one of these examples. But essentially, it's as if you would say, I'm going to make sure that for any matrix around the low rank approximation within a ball, my solution is feasible. And it turns out that A is within that ball. So you know that X you generate this way will be feasible for that way. And this problem here is a very simple conic programming problem. So you might wonder why I'm in this workshop. It's because due to the low rank spectral nature of these approximation, you end up with a second order cone type of problem, which again you can exploit the low rank structure in an explicit way, or in an implicit way you can simply say, well, any LP algorithm would require you to form this matrix vector multiply, and so it's understandable that we can gain a lot. So I don't have any examples for that last thing. It's in the works, and yeah.
I'm not sure I got the point. So you said before that in the LP case alone, forget about the robust part.
Yeah.
Then somehow that didn't work very well. So why this will? Somehow what?
Yeah. The thing is, yeah. All I'm saying is that if you just in statistics, for example, you can just say, here's the data, I compress it to a low rank, and I run with it. I forget that it was. You can do that. I argue that it's statistically not the best idea, but it's okay. Here it's catastrophic, because if you brutally replace A by low rank, then you don't guarantee feasibility for the original problem that was your problem. And so I think that's why the low rank approximation idea, which is so prevalent in many fields, has not been applied to optimization yet. That I have not seen that, except when there is, for example, a QP and a matrix, a quadratic matrix that is low rank or factor model, that has been applied, but not in the feasibility case, because it just doesn't solve your problem even suboptimally. This solves the problem suboptimally. Now the question is, how much suboptimality do we lose? And I don't know. So there's a number of themes, among which is this idea of low rank is just one way to approximate.
So here, for example, in the examples you discussed, the matrices, you know more than just the fact that you have a low rank approximation of your matrix. You know that the matrix you're approximating is actually sparse. So you could potentially include that constraint as well in the robust version to narrow down the set over which you're making your problem over.
That's a good point. I didn't think about it.
Does that remain tractable, you think? Or?
It depends. BERT-CMAS has a way to handle robustness with constraints where you say how many the perturbation has limited cardinality.
Right.
So I think that's a very interesting. So among the further topics is what to do with sparse matrices, and in networks, what is the good approximation? Maybe low rank is not the best thing to approximate a network. And so, okay, so this is in the works, and I don't even have a draft to mention, but this is, yeah. Thank you.
Questions or comments for Laurent? We have a lot of time. Somehow there was a mismatch between the time and you had a whole hour. But yeah. Yeah.
Do you know anything about a matrix LASSO version of this?
So are you talking about the case when the response vector is a matrix?
And you would like to enforce, you would like it to be low rank rather than sparse, yeah.
Ah, okay. So when the variable, yes, it's actually very direct thing, in the sense that basically what you're talking about is something like that. But this term, this W might be a matrix, this Y is a matrix, and this is a different norm. then what you do here is you add the same term. Now what I don't know, so then
That's just the Frobenius norm on the matrix now?
this guy, yes. Let me think a little bit. No, it's a spectral norm.
Oh.
So it's this would be the nuclear norm, this would be the spectral norm. But I don't know if then you can prove this. Like if you can go through here, or just algorithmically you have to look at those problems and under the hood see where you have matrix vector multiplies.
So in this reformulation, somehow, when you write the one in the bottom, right? You write S as a minimum of this, and somehow S and Z they appear in
Right.
you actually need to write it. I mean, somehow in there, I can replace S by any optimal solution. Somehow I'm solving those two things simultaneously, right?
Or in parallel, yeah. They're independent. This variable is independent from W. So you first solve a least squares problem, and
I see,
basically
just for
the
low
notation
one,
is
just for one of the factors.
yeah, one
so
column,
I
yeah.
see. And then the solution I plug it in. On
Right.
the other.
So this has only k variables. It's a very skewed problem, very fast, and this is also a very skewed problem, but in the other direction. So I'm not sure how to get this decomposition for all the similar problems, but for the LP case there is one, for the QP there is one, and for this one there is one. So it's
So this doesn't hold for general convex problems or something like this.
sorry?
This does not hold for a general convex problem.
Okay, so for general convex problems, I'm not sure they have, but essentially, yeah, yeah. Thank you. So for a general, let's say for this problem, which covers pretty much a lot of things, F being convex, so there's essentially, if you go and look at this guy. A low rank is the low rank approximation. This guy is only tractable for some F, and I don't know exactly but there is more generality to this. So for example, if F is the indicator function of some kind of polytope, it works.
Other questions or comments? Let's thank Laurent.